These massive towers, which are a staple of nuclear power plants, are built to do only one thing: to throw away tons of heat from the reactor core into the air. It's a crazy waste. But what if I told you that we could use all that wasted energy to produce clean drinking water instead? Today we're talking about nuclear desalination, what it is, how it works, and why a single nuclear desalination plant has never been built in the US. Let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Scarcity by Lutron. So what is nuclear desalination and why does it make so much sense? Nuclear desalination is simply hooking up a nuclear reactor to a desalination plant. The reactor provides a massive amount of reliable carbon-free energy that desalination needs. It's a no-brainer because a nuclear reactor produces massive amounts of heat and electricity, both of which we can use for desalination. You're also using a clean 24/7 energy-dense power source to tackle one of humanity's biggest challenges: freshwater scarcity. But how do you even hook up a nuclear reactor to a desalination plant? Well, there's about 3 potential ways to do it. The first is actually very common. The nuclear plant just makes electricity, and that electricity runs a reverse osmosis desalination plant, the most common type. Another setup is to use the nuclear reactor's heat to boil water and then condense the vapor as clean drinking water. In this case, the nuclear power plant doesn't generate any power, only water. And then there's pathway number 3. We'll call that the forbidden way. If you watch our previous videos on desalination, you're probably thinking that there's more direct and simple, almost obvious ways to desalinate water with a nuclear power plant. A few weeks ago, we looked at a solar desalination company called Sol Desal in Australia. Instead of a closed loop to run a steam turbine like most turbines around the world, you just A, use a heat source to boil seawater directly on one side, B, run the turbine with that steam, and C, condense the steam at the end as pure water, but instead of running it back into the boiler in a closed loop, you use it as drinking water. As we talked about in that video, there is one giant show-stopping reason this isn't typically done. It's called the brine carryover effect, which could destroy the turbine like shooting it with a sandblaster. But if they pull it off for concentrated solar, there's no reason it wouldn't work for nuclear heat. Solving this is a billion-dollar problem, and for a nuclear reactor, the complexity is even higher. So for now, this path is off the table. But there's also a way to get the best of both worlds, which brings us back to those massive cooling towers we were talking about before. A big traditional nuclear power plant at its heart is a giant steam engine. But like all steam engines, it's not perfectly efficient. About 2/3 of the thermal energy it creates is lost as waste heat, just dumped into the atmosphere using those huge cooling towers. But what if you use that waste heat for something productive? And that's what the third pathway is all about. You can take that low-grade steam after it's already spun the main turbine to generate electricity, and instead of just condensing it, you pipe it over to a desalination plant. Use the steam to heat up seawater in a process called multi-effect distillation, which is a brilliant way to make thermal desalination much more efficient. You literally spray preheated seawater onto hot pipes where the low-grade steam circulates inside an enclosed chamber. Parts of the sprayed seawater vaporizes, and the new hot steam gets piped to a second chamber where the concentrated salt water from the first chamber is sprayed again, turning more water into steam and getting piped to the next chamber, and so on until it loses as much heat as possible and you have pure fresh water. What's amazing about this path is that you can still generate electricity while using all the waste to desalinate seawater. So you generate clean drinking water instead of blowing off steam into the air. It's just brilliantly simple. Although there is a major caveat that we'll get to later in the video. See if you can guess what it is and leave a comment below. So let's get back to the 2 more viable paths: electricity for reverse osmosis and waste heat for multi-effect distillation, or MED. Which is better? Let's set a benchmark. We'll use a modern 100 megawatt equivalent molten salt small modular reactor, or SMR. Molten salt reactors are super efficient. They run at very high temperatures, so we'll assume a 45% thermal efficiency. This means to generate 100 megawatts equivalent of electricity, our reactor needs to produce about 222 megawatts of total heat. A modern RO plant needs about 4.5 kilowatt hours of electricity to make 1 cubic meter of water. Our 100 megawatt plant generates 100,000 kilowatts 24 hours a day, so 2.4 million kilowatt hours per day divided by 4.5 is about 533,000 cubic meters of fresh water each and every day. That's a lot of water, but we've used all of our electricity to do it, so we have zero power left to sell to the grid. Smart solutions like combining nuclear power and desalination can be a game changer. And speaking of smart solutions, our sponsor this week, Scarcity by Lutron, is helping us take our net zero home to the next level. While most smart home devices are fighting for space on crowded Wi-Fi networks, Caseta by Lutron uses their Clear Connect technology at lower frequencies that are practically interference-free. Setting up their smart hub and adding new switches and dimmers is a breeze, and their smart home app is clear and easy to use. But my favorite feature is that it's auto-detected in Home Assistant, and it brings all your devices over with just a click. So my entire home automation system runs securely and locally. And if you live in an older home like I do, you'll love that certain Lutron switches work without neutral wire. That means no rewiring and no expensive electrical work. We recently even added Caseta smart shades to our bedroom. We have them programmed to close automatically at sunset and open at 7 a.m. during the school week for the boys and 9 a.m. on the weekends. They install in minutes, the batteries last years, and I can't recommend them enough. After 55 years in the lighting control business, Lutron is the gold standard for quality and reliability. So if you're looking to build a smarter home, Caseta by Lutron has to be tops on your list. So check out their amazing line of products for the best prices today using our links in the description. Huge thanks to Lutron and you. Now back to the show. Now let's run path 2, MED with cogeneration. This is where it gets smart. We're still making 100 megawatts of electricity, but remember, that's only using 100 megawatts of our total 222 megawatts of heat. That leaves 122 megawatts of waste heat. An efficient MED plant needs around 7.5 kilowatt hours of thermal energy to make 1 cubic meter of water. Our waste heat provides 122,000 kilowatt hours, 24 hours a day, for a total of 2.9 million kilowatt hours of thermal energy per day. So 2.9 million kilowatt hours divided by 7.5 equals around 455,500 cubic meters of fresh water per day. So to clarify, path 1 gives us 533,000 cubic meters of water a day and zero electricity. Path 2 gives us 455,000 million cubic meters of water a day, only about 15% less, plus the original 100 megawatts of electricity to sell to the grid. How's that even possible? Well, it's the magic of cogeneration. Path 1 is thermodynamically inefficient. You take 222 megawatts of heat and turn it into 100 megawatts of usable electricity. And then you use that 100 megawatts of electricity to produce fresh water. And in path 2, we're just using the waste heat. So the original electricity generation is still there and we're harnessing that waste otherwise. But what if we combine both approaches? What if we took the 100 megawatts and used it to run a reverse osmosis plant while using the waste heat to run the MED plant? Well, then we could produce 1 million cubic meters of fresh water per day, or roughly 260 million gallons, enough for over 860,000 American homes. This is why the international consensus around nuclear desalination is that a hybrid plant that does both is the clear winner. If I'm honest, when I think about these systems, I approach it as a pure engineer, thinking about the system efficiency and productivity, and not as much from like the business perspective. But after years of doing this and covering so many different technologies, I've realized cost just matters, sometimes much more than efficiency, simplicity, or elegance. And when it comes to cost, comparing these different approaches to nuclear desalination isn't that simple. When you have one plant making 2 or more valuable things like electricity and water, how do you split the bill fairly? It turns out this is a pretty classic accounting problem. Think about it. The biggest cost is the nuclear reactor itself, plus the fuel, the staff, and the maintenance. How much of that multi-billion-dollar price tag should count toward the electricity, and how much should count toward the water? And this isn't just semantics. How you slice this pie dramatically changes how much each product appears to cost. I found this really cool tool that's free to use and you can try out for yourselves. It's the Desalination Economic Evaluation Program, aka DEEP, from the International Atomic Energy Agency. I'll leave a link to it here in the description. But even using DEEP lets you choose different cost allocation methods, and the results vary, like a lot. There are a couple of ways to go about it. You have the power credit method. Here you prioritize energy generation and give it a standard low cost and push all the rest of the cost to the water generation. And then you have the heat water credit method, which is the opposite. And by the way, you should know, this is what companies who want to make their water prices look cheaper use. This method alone can make the water costs look 25 to 30% cheaper than the power credit method just by changing the accounting. This exact issue came up actually when we looked at Sol Desal in Australia for our solar desalination video. We talked with the founders about how they allocated costs between power, water, and their third product, salt. They prioritized making the water cheap to compete in the water market. Their LCOE ended up higher, but still competitive, and the salt was treated mostly as a bonus byproduct to achieve zero liquid discharge rather than a primary cost bearer. It proves that the cost of Code-generated water or power isn't a fixed number. It depends entirely on the accounting choices you make based on your business's priorities. So we ran a couple of different simulations here, and it turns out that the nuclear plus reverse osmosis configuration, which is case 1 here in this graph, offers the lowest levelized cost of water, while also providing electricity at a competitive levelized cost of energy. But the MED plus reverse osmosis offers a good trade-off between cost and water production. So path 2 is the clear engineering choice, but what would it take to solve a real chunk of the global water crisis? Let's do the math for 500 million people. The global average of water use is around 170 liters per day, or 0.7 cubic meters. So 500 million people would need 85 million cubic meters of fresh water each and every day. Our single 100 megawatt SMR using path 2 generates almost 1 million per day. So then to provide water for 500 million people, we would need 85 of our 100 megawatt small modular reactors devoted just to water production. But what about the fuel? A conventional 1,000 megawatt reactor needs about 163 tons of natural uranium per year. Our 100 megawatt SMR is 1/10 the size, so it needs around 16.3 tons of uranium per year. So for all of our 85 reactors, our total annual fuel bill is about 1,386 tons of natural uranium per year. Now that sounds like a lot, but is it? The IAEA and the World Nuclear Association report that our known recoverable uranium reserves are around 5.9 million tons. So then that means with our known reserves, we have enough fuel for nearly 5,000 years of pure fresh water. So yeah, we have enough. And that's before we even talk about the next gen breeder reactors that create more fuel than they consume by using thorium, which is 3 to 4 times more abundant. From a resource and engineering standpoint, this is a completely feasible possibility. This sounds great. This sounds like this could solve our freshwater problem. So why aren't we doing it? While the Soviets were building their successful plants in Kazakhstan, and Japan and India were programmatically adding small working units to their own reactors, the US in the 1960s had a different approach. We didn't want to just build a plant, we wanted to build a newplex. The most famous was the Bolsa Island project off the coast of California. The plan was to build a 43-acre man-made island to house 2 massive nuclear reactors that would generate 1,800 megawatts of power and pump out 150 million gallons of fresh water every single day. And it was never built. But it wasn't a failure of engineering. The math worked. It was a failure of governance. The project collapsed under our own bureaucratic weight, a complex mess of competing federal agencies, regional water districts, and private utilities who couldn't agree on the finances or the risk. It was a classic case of the revolutionary do-it-all-at-once vision failing, while the evolutionary one step at a time approach succeeded elsewhere. For decades, that's where the story stalled. The capital cost of a giant gigawatt-scale reactor was just too high to justify for a desalination project. But now a new technology is completely rewriting the economic rulebook: small modular reactors, or SMRs. SMRs are the game changer because they fix the exact problem that killed Bolsa Island. They aren't $20 billion mega projects. They are smaller with lower upfront capital cost. They are factory built and shipped to the site, which means faster construction and better quality control. They are scalable. You can start with one SMR and add a second or a third when the demand grows. Their small footprint makes them flexible. They can be built in remote areas or right where you need them. Russia has already built the academic Lomonosov, a floating nuclear power plant. It's currently moored in the Arctic, powering a remote town, and it has an onboard RO desalination system that produces 40,000 cubic meters of fresh water a day. And the demand is exploding. The water-starved Middle East is all in. Jordan, Saudi Arabia, and Egypt are all in advanced planning stages with the IAEA to use SMRs to power massive new desalination projects. So SMRs finally can make this technology viable. But there are 2 final hurdles we always have to talk about with nuclear: the cost and the fear. First, the cost. Nuclear power plants are notoriously expensive and take years to approve, fund, and build. Second, the fear. This is the real barrier. The first question everyone asks is the water radioactive? Let's be really clear about this one. The answer is an emphatic no. The design makes it physically impossible. The reactor's primary coolant is in a sealed loop. It heats a second loop of water. That second loop then heats the seawater. There are multiple robust steel barriers between the reactor and the water you'd ever drink. Here's the analogy. Your car's engine is full of toxic hot gas, but your air conditioner blows clean, cold air. They're connected by heat exchangers, but the fumes never mix with the air blowing on your face. In fact, these plants are engineered so the clean water is kept at a higher pressure than the reactor side steam. If a leak ever happened, the clean water would leak into the reactor loop and not the other way around. We are facing a future defined by water scarcity and a changing climate. Nuclear desalination isn't a new or untested idea. It's a mature, proven technology with decades of safe, real-world operation. The old, centralized mega projects failed because they were too big and too complex. But the next generation of small, cheaper, modular reactors might finally make this all work out. We have a way to provide stable carbon-free electricity in vast amounts of fresh water, all from one machine. My own calculations show that using the waste heat is almost twice as efficient as just using the electricity, and that we have enough known uranium to power a water solution for 500 million people for nearly 5,000 years. It's no longer a question of technical feasibility. It's more a question about public and private collaboration and effective governance, which isn't a guarantee. But what do you think? What do you think about the future of nuclear desalination? Were you as surprised as I was that we've actually already done this before? I really didn't know that until starting this video. Sound off in the comments below. So until next week, check out our Discord and our newsletter. We'll have links in the description to join us in a more private fashion. And we'll see you next week. I'm Vinci. Thank you so much for watching.